EI, take this equal to constant. And the horizontal now length of member BC is 20 feet. And the height of the column, it is 12 feet now. Now again, if we ignore the axial effects, it's a 2 degrees indeterminate problem. That is theta at B and theta at C. Now how we are going to solve this problem? So first we identify the unknown giant displacements, which is D1 and D2 here, D1 and D2. Corresponding to them in the actual structure, we don't have any moment at B, we don't have any moment at C. So AD1 and AD2, they are becoming 0 and 0. D1 and D2, these are our unknowns. Now here you see the basic kinematic determinant structure. B we have clamped and C we have clamped. We have stopped the rotations at B and C. And this is our restraint structure. Now ADL matrix, so we are coming to step number 2 now. It's a basic determinant structure now. So we have separated AB and BC at joint B. We have split them into 2 members now. We have opened the joint. Now at AB, now under the actual load, this 5 kip load, we need to find out the member and actions now. So member and moment will be PL divided by 8. So PL divided by 8 is becoming 7.5 kip foot. And this is also 7.5 kip foot. The horizontal now reaction here, it will be 5 divided by 2. Why 5 divided by 2? Because we don't have any unbalanced moment and it is at the mid. So half is coming to support B and half is coming to support A. 2.5, 2.5. From where this 10 is coming, we'll discuss this. Now this 2.5, it can travel towards support C, where we have a hinge support now. So 2.5 here now, to balance this, rightward directed, we are applying this 2.5, and here 2.5 now you see here leftward directed. So it travels from B to this joint B to support C now. So all the member and actions we found here. Still this we need to discuss now, this axial force 10 kip. Now coming to this member BC, WL square divided by 12. W is 1, L is 20, so divide by 12, 33.3, 33.33 here also. Vertical, it is 1 times 20 divided by 2, so 10 kip and 10 kip are coming here. Now at joint B now, we are restraining only now the rotation here. Still it can slide upward, means it can transfer the load in this vertical direction. So this 10 kip, it was in upward direction. So at joint B in member AB, it will become in downward direction. This 10 kip is going to be balanced by 10 kip. And this, when we keep this member in equilibrium, so this 10 kip downward is going to be balanced by 10 kip in the upward direction. If you see now, each member is in equilibrium, each joint is in equilibrium, and now we are in a position to calculate our ADL matrix. So coming to ADL, one corresponding to this one location, we have clockwise 7.5 and we have counterclockwise 33.33. So 7.5 minus 33.33, which is coming equal to, here I can see some ADL one, it should not be 25, it should be something different than 25. So first let's now WL square divided by 12 we need to confirm. So 1 times 20 square and divided by 12. So it is coming 33.33 minus 1 and plus, if I do 7.5, so it is coming minus 28. So this is minus 28 point. Actually, we need to now change this to the actual number, which is minus 28.83. So this is actually minus 25. Anyways, you can make the changes here and we will check in the coming one that it should be minus 25.83. And this one is 33.33. So ADL2 is coming from here, which is corresponding to D2. So we now completed the ADL matrix. Coming to the stiffness now, so step number 3 we are going. And what we do now, first we apply corresponding to one location a unit rotation and we prevented at this 2. And then corresponding to 2 we give a unit rotation and we prevented at location 1. And this way both columns of the stiffness matrix are generated. So first a unit rotation is applied, that is we keep D1 is equal to 1 and D2 is equal to 0 and we compute the values of S11 and S21. So here now unit rotation as we did in the previous problem. Unit rotation is given. This member BC how it rotates and how AB rotates. So you can see from here 4 EI or 20. So 0.2 this will become 0.1 here and the balancing couple you can find out. This was downward. For member AB it will become upward and here it will become downward again. So this downward will become downward. Similarly here it is going to travel here and this way you can find out all the member and actions. Similarly for member AB here the moment generated will be 4 EI divided by 12. L is 12 this one and here this is the member and moment by half amount of this one. This is the balancing couple. It was clockwise, so this should be counterclockwise. Now this leftward directed force, it will become rightward directed for member BC and here it is going to be balanced by this 1.4. So this 0.4 to how it is traveling here. So you have this all the member and actions, and remember this will give you the first column of the stiffness matrix and it will give you the first column of the AMD matrix also. So now S11 will become corresponding to this one we were having clockwise now D1. So 0.2 plus 0.333. This will become your S11 and S21 will become equal to 0.1 EI. And here you see this is 0.533 and this is 0.1 EI. Coming now to the application of the theta is equal to 1 to D2 location. Here that is applied theta is equal to 1. This is 4 EI over theta, 2 EI over theta, and this is the balancing moment and it is traveling down to this support. Here we don't have anything, so this horizontal reaction here is going to be 0. And this will give you the second column of the stiffness matrix as well as the second column of the AMD matrix. Now S12 will become equal to 0.1 EI, which must be equal to S22, and S22 is equal to 0.2 EI. So now the second column is complete, and now we can write this in a nice form. So this S is equal to EI times 0.533, 0.1, and 0.2. So this is the stiffness matrix. Now we will write the equilibrium equation. This is the standard form of the two simultaneous equations. This is how we write them in the matrix form. And this is the equilibrium equation. And this is the rearrangement of equilibrium equation in order to find out the unknown joint displacement. We put the values in, we solve it, and D1 and D2 are found. Again, if you see D2 is coming negative, it means our assumed direction was wrong. But still now you will have to live with these negative signs now for the rest of the calculations. Here again we are taking AB. We are taking now all the member end actions for member A. This is the starting end and B is the ending end. Vertical. Now here, look, it's your choice. There we took the vertical as first one. Here I am taking the horizontal as first one. So this is, and accordingly then you will have to now follow all the directions. So AM1 is horizontal, but again rightward, upward, and clockwise I am taking positive. So AM1, 2, 3, 4, 5, 6, all these. Now I'm labeling this accordingly. Now AML will be now labeled accordingly, and AMDs will be labeled accordingly, and accordingly the values will be picked from their previous locations now. So AML values, we will grab them from where we generated our ADL matrix. We go to the same member AB there, and AML corresponding value is now minus 2.5, and you can see it here in the matrix. AML2, it is 10, so it is 10. AML3, it is clockwise. Here we have counterclockwise, so it is minus 7.5. AML4, it is minus 2.5, so minus 2.5. Here you see AML5, it is minus 10 now, so minus 10, and AML6, it is 7.5, so it is 7.5. Next, now we go to the AMD. First column is generated from where we generate, who have had this first column of the stiffness matrix now, which was from the application of the theta is equal to 1 corresponding to D1 now. And we are interested only in the AB member values. AMD11, so from here you can see it is 0.042. AMD21, it is minus 0.15. AMD31, it is 0.67. Similarly, you can grab the values from here also. Second column of the AMD matrix for this, here from these values you will have to generate now. So how much is AMD12? It is 0. We don't have anything. AMD22, it is minus 0.015. AMD32, it is 0. We don't have movement. And similarly for the other end, corresponding values you can pick. And here you see now all these zeros and all these things. So this is how we make the AMD matrix for a particular member. Next, now we put them in this equation. AM is equal to AML plus AMD times AD, and we solve it, and these are all those member inductions. This was now the horizontal reaction. Now this is the vertical, and this is the moment. And accordingly, you can put them on this sketch now. This is now a little bit here. We have this. This is, look, this was our AM1. Right, this is our, so it's a slight mistake now. So this has to be AM1, and here we have this AM2. And just to make sure that we are, AM1 should be equal to 1.193. 1.193, you can see here. AM2, which is the vertical, it is 11.84, so 11.84 here we are writing. And similarly, you need to adjust these values also. So this is our 4, and this is now in this case our 5. Once you check your baseline, so you cannot change them later on, you cannot change them. Now, if you see, to draw the shear force and bending moment diagram, we need to put the actual load on this also. So these are just the member inductions now. So here we have put that 5 kilopascal. Because of this 1.93, we are coming to the right. We don't have any load up to this point. Then because of this 5, we are going further to the right. We don't have any load, so it is constant. And because of this 6.5, it is closes then. So this is the shear force diagram. The bending moment diagram 7 point, which is coming to this way. And this this diagram is not correct now, the bending moment diagram. It should be changing here because of this situation. First one, and it should be changing its slope here because of this. So anyways, you can go and you can verify all these things. Now, coming to this step number 5, and the step number 5, we are repeating this for member BC now. So AM1, 2, and 3, these are becoming our reference labels and reference directions also. AM4, AM5, and AM6. And equation again, AM is equal to AML plus AMD times D. So this is now AML1, 2, 3, 4, 5, you can see. from where we are going to get those values from where we generated the ADL matrix. So corresponding to AML1, we have this plus 2.5. So 2.5 here you can see. AML2 is 10, so 10 here you can see. AML3, this is in opposite direction, so minus 33.33 you can see. AML4, it is minus 2.5, so you can see AML5 is 10. So 10 here you see, and AML6 the same direction, so plus 33.33 you can see. Next, now AMD matrix we need to generate. So we go to the member and to the location where we generated the first column of the stiffness matrix now. So AMD11 now is how much it is. This is to the left, so for BC it will become to the right. To the right means it is in the same direction, so it will become 0.042 now. For AMD21 it is downward, so it will become negative, and 0.05. AMD31 it will become 0.2, and so on for this, and you can pick the appropriate values from here, from this location. Then second column of the AMD matrix for the BC, we generate from where we generated the second column of the
क्लास खत्म छो
ना क्लास था सर्वला नेट की मसला था चलता
यार हमें मसला था नेट वाला अगर अटेंडेंस लेके बोला गो यार
तेरा सुमाम उसको फिक्शन लगे मसला था यार जामाते में करने से लगा वैसे तो
यार नेट मसला टोलो था खुदा नो मानी अन अगस्त का ना वेवा
पर ये प्रो इलाज किया
वाला
संगा
दिशा ननन कसांडर कम दी